are looking at descriptions of chemical reactions. We're writing down equations for those chemical reactions. We're balancing those equations. And then we're doing some calculations where we find how much of one or another quantity we need or we form based on being given something else. We can always figure that out from the mole ratios that we find by balancing the equation. All right? And we usually see it in this form because we're dealing with grams in the lab, where we start with grams, we need to convert to moles, then go to whatever moles of the other thing, and then grams of the other thing. So it's grams to moles, moles to moles, moles to grams that we do every time. And so here on the sheet, you see there's a bunch of problems doing basically the same thing. Here, pass it back to. So let's first start. The first couple here on the, I guess it's the front page. I just kind of randomly put stuff on them here. These top ones are all just balancing equations. So if you need a little more practice with that, there's that. We're going to start today halfway down, looking at this reaction of aluminum with hydrochloric acid. So consider the following reaction. Let me pull this up here, wherever it is. There we go. You've got aluminum reacting with HCl. Here's a balanced reaction for you. Now, another thing that you should be able to do, we'll get into this later with some of the other ones, is instead of being given a balanced equation like this, I might say, consider the reaction where aluminum reacts with hydrochloric acid, forming hydrogen gas and aluminum chloride. And you should be able to write down that equation and balance it appropriately, just given the names of those compounds. So here we have it for you, and it's already balanced. Because 2 aluminum atoms react with 6 molecules of HCl, how many HCl molecules will react with each of the following? So if we've got, instead of 2 atoms, if we have 12, how many HCl's do we need? Does anybody see that right off? How'd you come up with 36? Okay. Right, so this is proportional. So whatever we do to the first one, we have to do to the other one. So that's one way to look at it, is 12 is 2 times 6. So then we also need 6 times 6 to complete that proportion. Another way to look at it is the ratio of 2 to 6 is like 1 to 3. So we're always going to need 3 times as many HCl's as we do aluminums. All right, so if we have 12, we're going to need 3 times that, or 36. And then the other way to do it, if you can't just see it, which is fine, is to actually write it down like a unit conversion problem. So we take 12 atoms of aluminum, and we multiply it by a conversion where we put atoms of aluminum on the bottom, and then atoms of, or molecules of HCl on the top. Atoms of aluminum cancel, and we end up with molecules of HCl. But to find the numbers that go in there, we go back to the equation and we see, okay, we've got 2 atoms of aluminum for 6 molecules of HCl. So if our atoms of aluminum cancel, we end up with 36 molecules of HCl. All right, what if we have 24 atoms of aluminum instead? Then how many molecules of HCl do we need? $72, right. And once again, we have the same ratio. It's that 1 to 3 ratio. So 24 to 72. 72 is 3 times 24. Again, we could plug that in here and say 24 atoms of aluminum times 6 to 2 would give us 72. What about 100 atoms? 300, right. Now we can also do this in some of our quantity words. So when we use other words to express particular quantities. If we do this from a dozen atoms of aluminum, how many dozen atoms of HCl do we need? Well, 36 atoms, but how many dozen then? 3 dozen. So we see how we do this? We still have the same ratio, 1 to 3. So 1 dozen aluminums needs 3 dozen HCl's, which of course is the same as saying 12 and 36. The reason it throws dozen in there is because then we're going to look at moles, and moles work the same way. If we start with a mole of aluminum, how much HCl do we need? 3 moles. 3 moles, right? And then if we have 3 moles of aluminum, we need? Got a lot of numbers that aren't right. We got one that is? 9, right. So again, the 1 to 3 ratio. And we can write that the same way. So we can go 3 moles of aluminum times the equation tells us there are 6 moles of HCl for every 2 moles of aluminum. If we evaluate that, that means we need 9 moles of HCl.
Wait, for D, what was true? For a dozen?
Mm-hmm.
How much is it?
3 dozen.
3 dozen, okay.
All right. Same thing. So we can do the same procedure that way. We can say 1 dozen aluminum times, whoops.
So the numbers stay the same, that is the one.
Right. The numbers come from the equation, the balanced equation, which is again why the equation needs to be properly balanced first. And then we can figure out whether we're talking in molecules, in atoms, in dozens, in moles. As long as it's a count, not a measurement, but a count, we can use whatever kind of count we want. So if it said 10 grams of aluminum, we couldn't do this exactly. We'd have to convert those grams to moles first, because grams isn't a counting, grams is a measurement. But as long as we have a counting thing like atoms, molecules, moles, dozens, whatever, then we can do this directly. All right, so now you try one. The next one, same type of problem, just with, where is it here? A different reaction and a different ratio. So this one you probably are going to need to set up a calculation because it's not as obvious as a ratio. It's a 4 to 5 ratio instead of just a 1 to 3. But see if you can figure out how many oxygen molecules you're going to need for each of these 5 quantities of ammonia molecules. So see if you can set these up in the same way as we did the previous one, just with the different numbers from this equation. Yeah, I guess everybody has this, right? So we don't need to put that up there. So look at where we get those numbers in the previous one from the equation, and now we're going to do the same things in this equation. Sorry, I'll be right back. All right, the next one. Yeah. You should have it on your paper there. Yep, it's just on the bottom there. All right. Does anybody figure out any of these yet? I think.
First one,
What'd you get for the first one?
15.
15? Is that what other people got? Something different? Yeah, 15. All right, good. How'd you figure that?
I do my own way. I just did it 5 times 3,
5 times 3.
right? Because,
Okay.
yeah.
Because 12 is 4 times 3.
Yeah.
So, okay. Yeah, that's great. And when it works out nicely, there's no problem doing that kind of thing. As we'll see in a little bit, sometimes the numbers get a little bit trickier. So that'll be fine. But the way to set it up like this is to take the same idea. So we've got 12 NH3 times 4 of these to 5 of these, or 5 to 4. And that's going to be, it's going to give us 15O2. All right. And so you can use the same conversion with any of these quantities. You just change the quantity right here. So for 1 dozen ammonia, we're going to have 5 over 4 times 1, or 1.25 oxygen, and so on. And for 4, we're going to have 5. So that's directly like the equation. All right, so let's see what happens with this when we have to start putting some other quantities in there instead. So let's flip the paper over. And I want you to go about this far down the page. You see something that talks about butane. Actually, no, we're going to start right at the top, the thing about zinc and cadmium. Here we go. And we're just going to look at the first one for now, but the procedure is the same for the second one. We're going to look at the number of moles of hydrogen produced by the reaction of aqueous HCl with 2.48 grams of metallic zinc or cadmium. So this is like the reaction we did in lab on Tuesday where you put the pieces of metal into the HCl. Same reaction here. So first we have to actually write down that reaction. So what's going to be a reactant here? What are our reactants? We put on the left. HCl. And what's that reacting with in the first case here? Zinc, right? And what is that producing? Yep, that's going to be producing hydrogen gas. Because it's telling us that. And then we know it has to produce something else too. What else does it have to produce? Why do we know that hydrogen isn't the only product of this reaction?
Because there's other elements on the left.
Yeah, there's other elements on the left, so we have to balance those out too. So the other thing it produces must be a compound of zinc and chloride. And so the compound of zinc and chloride, zinc is +2, so it needs 2 chlorides to balance it out. Whoops, not gas.
About the,
So is that balanced?
No,
What do we have to do to balance it?
balance the hydrogen and the chlorides and the chlorine.
Yeah, so we've got 2 CLs on the left, 1 on the right. So that means we need a 2 over here. And that should do it, right? Now it's balanced. So that was easy enough.
How do you know zinc and the
Chlorides.
chlorine too was AQ?
Because we don't really, I mean, I knew that. I wouldn't necessarily expect you to. It's in solution. One thing you might remember from the lab on Tuesday, when that stuff went in that HCl, there wasn't any like solid or anything left, so it must have been in solution.
yeah, the
metal,
structure is-
right.
And where did you get that from, that zinc and the chloride? Where did it come from?
Well, we knew that the problem told us we produced hydrogen, but we knew that there must be some other stuff too, because we can't magically make zinc and chloride disappear in the reaction. So the remaining product must have been a compound of zinc and chloride. And the only compound of zinc and chloride, which is ZnCl2.
So we're kind of know that.
Yeah, you kind of have to know that to finish up this equation. That's not one that we talked about knowing, so like zinc being +2, but it is. So that's the only possibility. Okay, so let's continue on with what we're asked here. What is the number of moles of hydrogen produced by the reaction of aqueous HCl with 2.48 grams of metallic zinc? So we're told here that we've got 2.48 grams of this, and we want to know how much hydrogen do we produce. That's what the question's asking, right? How much hydrogen do we produce from the 2.48 grams of zinc? Well, to figure that out, we need to, we can't do what we just did before because we don't have a counting unit of zinc yet. We only have a measurement unit in grams. So we have to convert that grams to moles, and then we can do what we did before to find the moles of hydrogen. So how do we convert 2.48 grams of zinc into moles? Yeah, we're going to need to use the molar mass, right? So we take 2.48 grams of zinc, and we need the grams of zinc per mole. of zinc. How do we find the number of grams per mole? Right, the molar mass or the atomic mass on the periodic table. So it's 65, let's say 65.4 grams. And we calculate that out. And that tells us that 2.48 grams gives us 0.038 moles of zinc. So now that we have moles, we can figure out how many moles of hydrogen we're going to form based on the ratio in the equation. So what's the molar ratio of zinc to hydrogen in our chemical equation?
2 hydrogen.
Just in the equation, just what's the ratio based on the numbers, based on the coefficients in the equation? How many zinc atoms produce how many hydrogen molecules?
1, 2.
Close, it's actually 1 to 1. Right, there's 2 hydrogen atoms, but there's one of these for every one of these. So every one zinc atom in this reaction with its HCl produces 1 H2 molecule.
So you compare the 100 product to the reaction?
Right, or whatever you're being asked to do. So in this case, we can take our 0.038 moles of zinc, and we can figure out by the equation how many moles of zinc to how many moles of hydrogen gas. The equation tells us that's 1 to 1. So that means that we produce 0.038 moles of H2. Now, what if we wanted to know how many grams of H2 that is? How would we figure that out?
Multiply the moles to the atomic mass.
Right. So we need to take this moles of hydrogen and convert it to grams by the molar mass. Molar mass of hydrogen is 2 because each hydrogen is 1 and there's 2 of them. So that's 2 grams per mole. That means that we would expect to make 0.076 grams of H2. In this reaction. So that initial 2.48 grams of zinc, if it's reacted with all of the HCl that it needs, will end up producing 0.076 grams of H2. Of what?
I thought we only had 1 hydrogen.
The ratio is 1 to 1. But depending on how much we start with, that will tell us how much we ultimately form. All right, we'll leave that one there for now. And let's go on to the middle bit here. Yeah, so this one that's talking about H3PO4. I have that somewhere. Here it is. All right, calculate the number of moles of H3PO4 that will react with 1.29 moles of sodium hydroxide in aqueous solution to form sodium phosphate. All right. This one also has a missing reagent in it, so we'll see if we can figure that out. So our H3PO4 is reacting aqueous with sodium hydroxide. forming sodium phosphate. Again, you wouldn't necessarily know that that's going to be aqueous. And what else has to be there? This one's a little bit tricky. Yeah, hydrogen for sure. And we're going to talk about types of reactions. I don't know if you've gotten through the rest of the lab questions yet. Yeah, you're going to need some oxygen too. So what you're going to need here is to realize that this is a type of reaction where the two things kind of switch partners. So the phosphorus was with the phosphate was with the hydrogen, and the hydroxide was with the sodium. The other side, you've got the phosphate with the sodium, so that means the hydroxide goes with the hydrogen. And what's the compound of hydroxide and hydrogen? HO and H would be water. And we'll get into that more in the next part when we talk about types of reactions. We'll be able to predict this a little bit better. Is that reaction balanced?
No.
No, I don't think so. Let's balance that. So we're going to need 3 of these, right? 3 of these. That does it. Okay, back to the question then. Calculate the number of, now we have a balanced equation. We can start dealing with these other types of questions. Calculate the number of moles of phosphoric acid that will react with 1.29 moles of sodium hydroxide in aqueous solution to form sodium phosphate. So how many moles of this do we need to react with 1.29 moles of that? Now we're given moles, the counting quantity, which means we can use the molar ratio from the equation to figure this out. So we can say 1.29 moles of sodium hydroxide. We want to cancel moles of sodium hydroxide, and we want to get moles of phosphoric acid. And how do we find the numbers that go in here? Yeah, looking at the numbers from the equation. So we've got 1 of these for every 3 of these. That's what the equation tells us. 1 phosphoric acid for 3 sodium hydroxides. And divide that by 3. And that's what, 0.43? Okay. So for every 1.29 moles of sodium hydroxide in this reaction, we need 0.43 moles of phosphoric acid to get them to react. We could use a similar technique and figure out how many moles of the others we make. And in fact, we can just do that by looking at it now that we've got these 3. If we need 0.43 of this for every 1.29 of this, how much of this do we make? How much of this do we make? How many moles of this are we going to make? Do we have to do another calculation, or can we just see it? It's just 0.43. Because we know that this is 1 to 1. So every one of these has to make 1 of these. Therefore, every 0.43 of these has to make 0.43 of these. So then how much of this do we make? 1.29, right? Because this is 1 to 1 or 3 to 3. So for every 3 of these, we need to make 3 of these. For every 1.29 of these, we make 1.29 of these.
And I was under the impression, because I mean, it combines, so the sodium combines with the phosphate, so that I was under the impression that you have to combine both, including the molar.
The masses will be different, and the masses will be additive, meaning the mass on one side has to equal the mass on the other side. But the moles don't necessarily. So you can have more moles of one. If you imagine a reaction where you have a bunch of molecules that all come together and make one, you're going to have a bunch of moles on one side and then just 1 mole on the other side because they all came together to make that one. So it's the mass must be additive, but not necessarily the moles. Maybe? No? All right, we'll keep working on it.
I still don't-
Okay, this is gonna take a lot of practice. Unfortunately, I have to cancel class early today because my kid's getting kicked out of school and I have to go get him. But we will return to this on Tuesday. My